All right, next up we have Rafal Szarecki. He will be presenting optimal routing versus route reflector VNF, reconcile the fire with water.
Good morning, everybody. It's nice to be here. It's my third NANOG and feel at home. Yeah, still good morning, especially for those from the West Coast. It's a time to start work. So let's start. I will talk today on that session about some implication of use the virtual route reflector, especially in the context of the routing optimality. So we start with like a definition why we are doing VNF, why we are virtualize network function, which is the route reflection function. What are the benefits we are looking after? And then we examine, I will go through the challenges with the route reflector implementation in the traditional environment and how we address it today, typically. And then try to reconcile these two things and see how we achieve the current optimality or current behavior while benefiting from the network function virtualization. So the route reflection is a function, right? We tend to think about route reflector as a device, as a node, but at the end of the day, it's a function we need in the network, and we can instantiate it as a virtual instance, as a software running in the virtual environment. And the natural place for the virtual machine is a data center. And data center is where it is. It's not where we want to have a data center from the route reflector perspective. It's where it is. So we have to live with that, and that's a very important point for my talk, because this is what we will fight against. At the same time, while we virtualize the route reflector, when we move it to the virtual environment, we want to ensure that it behaves in a way, from the routing perspective, in a way we expect from route reflector. So it selects the optimal path, not worse than it's today. And we don't want to have more problems with this session scaling or path scaling. That's a secondary order issue, but just keep in mind. Very, very traditional approach is to use the router, whatever the router is, use them to run a route reflector on top of this platform. But the point is, the router by design is optimized to do packet forwarding. Otherwise, it's not a router. Not for the data storage or processing. That's overhead. That's a cost of doing business for this kind of device. However, the route reflection function is critical, is very important. It takes a lot of resources, but not the forwarding resources. We have servers at the other end, right? We have which are designed for compute data, and it would be good to use it, and especially that if we consider efficiency, like cost of processing the prefix or cost of keeping the RIB, it's much lower on the x86 server platform. And that's even lower if we consider the virtual machines located in the data center environment. We can and VMs brings other values as well. Right? We can easier scale it up, we can easier migrate from one VM to another, etc. So, because route reflector by its nature, it's a cost of doing business, right? No of your customers is paying for better or worse route reflector. You need it to run your network, but you need it efficient, powerful, but at the same time, the optimization point for route reflector is always to find the cheapest way of doing things. That's why virtualization of the route reflector to virtual environment to the VMs seems to be attractive. Okay, how the root reflectors works in the, traditional network, right? We tend to, in very traditional approach, the root reflector function is either ported or running on path on the kind of aggregation or core router, or on the another router which is off the path. And due to optimization, path optimization, the slightly bigger network try to distribute the reflection on a regional basis in order to promote regional regionally local exit from the network. Some traditional approaches to use the retired router, which is not able to keep with the traffic we need to switch, to move them out of the data path and use them as a root reflector platform. But it doesn't actually help much because it's old router, so it's already dated CPU, limited memory. That's short time optimization. So the first optimization for the root reflector platform would be change the platform, right? Move from the router hardware, whatever, MX, Juniper, Cisco, whatever it is, to the server, to compute node, to appliance. And that's absolutely possible, especially nowadays when all vendors provides the software version of the router, either Juniper, Cisco, Alcatel, everybody Viata, everybody is doing that. But this change, it's not end of the story, right? There is a couple of things we are not gaining from that. We still need the interfaces to connect the server to the router, to the network. We still need to maintain this platform, right? It's a physical platform somewhere in the network, so we have to go there, we have to upgrade it, we have to maintain it. Even worse, this requires new skills to manage the platform. It's not a router, it's a server. It has some operating system, it has to be patched, etc. It's sysadmin skills which not every network operator, staff, person possess. And of course, the last but not least, the technology cycle in the server world is shorter. So very soon, the end of life, the hardware replacement cycle in the server is shorter than in the router. It's good because you always have the best of the breed and faster platform, but at the same time you have to manage upgrades and moving the software from one platform to another. The other dimension of the possible optimization of root reflection infrastructure is just centralized, limit the number of root reflectors. And that's not a new idea. And in context of virtual function or virtualization of root reflector, it's appealing, right? Because, hey, let's move all root reflectors to the data center, one or maybe two for redundancy. But then simple centralization to one node exposes some challenges. It's quite possible to do for VPNs, and many providers are doing this for VPN families, but it's not that popular for internet, even in the past. And there are two fundamental issues with the very centralized, let's say, single root reflector per whatever size of the network. It's a scaling challenge for session and for path, and we will examine it in a minute. And the other, even more important, is suboptimal routing as an effect of that. So first, to look closer to the session scaling problem, right? The network are bigger and bigger. They have bigger capacity, but it also has more and more nodes. So if we go extreme and say, oh, hey, one root reflector will serve all my edge routers, then we can end up with thousands of sessions. And that's a pressure on memory, not a big deal nowadays, but also on the CPU and on the communication path. We have to send the same information many times over the links which are next to the root reflector, especially the root reflector uplink. So that's why in today's network, especially internet route reflection infrastructure is kind of distributed or regionalized, because it mitigates the problem. You can see on the right side that the number of sessions is more linear, more piece when we distribute the route reflection system, and there is no black magic here. Very similar is the path scaling, right? The interesting observation is that from VPN perspective, it's not that big deal because for given VPN, the single prefix are multi-homed, but if we say multi-homed, it's usually 2. However, in the internet context, the big ISP has multiple sessions across the network, in many places on the network, but end of the day, there is tens of peers when they get the full table. That's especially for that's a case for the one who provides the transit service. And this is a pressure again on the CPU. We have more paths, there is a higher risk of the churn, there are always paths going in and out, withdraw, run-outs, and even they are not the best path. Software has to realize that this is something going on. And again, the regionalization of route reflectors. So having the route reflectors in the local scope, it's a kind of hierarchy, and building the hierarchy solves the problem. It's exactly the same math behind that and the session scaling. And then finally, the routing optimality problem. The route reflector, it follows BGP. So if we keep the add path aside, we will come back to this in a moment. In principle, BGP route reflector selects the one best path per prefix, and it's best from a route reflector's point of view, considering route reflector's position in the network, IGP view, topology, etc. It selects the one and advertises this to all and every of his client. So the route reflector client is not aware about alternative paths. It just knows the one given by route reflector, and they have to follow it. And this is not necessarily the best exit from the from the client perspective. It's just the best exit from the reflector. In L3 VPNs or L2 VPNs, VPLS, this problem is somehow solved by use of the PU by use of route distinguisher part of address, which is based on the originator loopback address. This creates the unique prefix from the route reflector point of view, and of course, if every prefix is unique, there is nothing to select. Every prefix is the best one. However, for internet, it doesn't happen. There is no route distinguisher. Instead, we have add path. But add path is not really good for routing optimization. It's a nice tool to provide the alternative path for the fast restoration or faster restoration of the traffic. But in order to be able to say, hey, it's optimal routing, we have to add all paths. If we add all paths, then we have, again, the scaling problem. And it's very, the scaling grows very fast with the route reflection and add path together. We can limit the size of the add path. Let's say add path, second best path. But then nobody says the second best path would be the optimal from route reflector perspective, from the client perspective. So again, the traditional answer to this problem is go regional route reflectors. That mitigates the problem. Of course, route reflector still selects the best exit from his point of view. It's not globally the most optimal one per every single client. It's a semi-optimal, but that's good enough. That's what we are doing today. That's a current status quo, and I'm not trying to exceed that. I'm just trying to match the current status quo of the optimality with the benefits of the virtualization of the root reflection function. So again, we are going back to the goals. We want to have the root reflector working in the virtual environment in data center, whenever data center is located. And there is an important assumption I did during the preparation for this talk, that the data center infrastructure may have L3 elements, which doesn't participate in the one network routing, IGP, BGP, whatever. That means that we have to somehow bypass this or overcome this problem to enable the root reflector to choose the best exit. And a small recap. In the BGP path selection process, we are in the middle of selection. We have very important step, and this step is that it says that the best path would be the one which has the lowest IGP cost to the next hop, right? And from now on, this would be the step against which we will do our design and against which I will try to explain how to play with that to achieve semi-optimal, regionally optimal routing. We start from we go through the example, and we start with the traditional network design. There is a country, whatever it is, not my home country. And in this country, we have 4 regions. We have 2 root reflector per region for internet, another 2 root reflector per region for the VPNs. So altogether it's 16. They are spread across the country, located in the network sites. This root reflector may or may not be maybe collocated with the core routers, or even implemented as a function on top of the core router. It doesn't matter. The important thing is that the data center are on the west and east, where the real estate is cheap. The power is cheap, space is cheap, labor is cheap, but it's not necessarily the most optimal place for the root reflector. So our goal is to move the functions, move the root reflection function from the network into the data center. And not necessarily consolidate root reflector, just have them where the compute resources are cheap. And for the geo-redundancy reason, in this picture, you see that there is a east and west data center. So from each region, one of the internet root reflector goes to the west data center, another to the east data center. However, we have to address the problem of lack of layer-free connectivity, or actually lack of IGP connectivity to the root reflector. And we want to keep the south region or north region to select the local exit point in the region as a best BGP path. So the proposal or the approach to do that is, yes, we have the virtual root reflector. It runs the BGP as usual. It has the same set of clients as the root reflector in a before scenario. So let's say south region clients are peering with a given root reflector instance. But there is this root reflector instance has also the so-called shadow routing context. It's nothing else than the additional RIB, routing information base, which in some way keep the topology and metrics information from the south region or north region, designated region point of view. I will use the south as an example during this explanation, because that's what the picture is showing. So this virtualized root reflector supposed to perform the BGP path selection based on the information not in the main RIB but in the other RIP. So we will go through the 3 elements of that. First is this shadow instance, right? We have to populate them with the topology information, with the metrics, and it's done through using the GRE tunnel, right? So we open the GRE tunnel, which payload is terminated in this routing instance, and we will run the IGP on top of it. So this way we will build the proper RIB. The another end of the tunnel is somewhere deep in the network. In this example, it's one of the core router in the south region. From IGP perspective, there is a couple of policies. We don't want this shadow instance to be on the shortest path for anything. So set the overload bit or bump the link metrics for the tunnel. Do not insert any route learned in the shadow instance into the forwarding table because there is no need. The only purpose of this instance is to have a routing information base used for the BGP next hop resolution. And we don't need anything else than loopbacks, right? The other end of the tunnel, I call this router shadow host, but you can call it whatever. We not need anything special here. Okay, GRE tunnel, that's one thing, but except of that, we run basic IGP on top of it, run BFD maybe if we need, bump the metrics, and potentially, for the security reason, we want to avoid the transit traffic entering this tunnel. Last part is a global instance of the virtual. So in the global instance, we have BGP running. And the global instance has a couple of the functions. First of all, the global instance is the one which has the routing toward the network. And because our assumption that we don't know what is the data center infrastructure, we cannot assume that IGP will go there. So static is good enough. It could be default, it could be aggregate toward loopbacks. We can use VRRP or if the data center provides, or use BFD. And this forwarding information, this static route, are used for 2 purposes. First of all, we use it to forward BGP packets from the BGP process down to the router, all clients in the designated region for that instance. And also we use that forwarding instances to forward the encapsulated tunnel packet, not the payload, but after encapsulation, to forward to the shadow host. That's important, and I will tell you why in the 2 slides forward. That was about forwarding. The BGP, which runs in this context, it learns the prefixes over the session from clients or from other route reflectors. That's a normal thing. But the next hop resolution, so the finding what is the metric toward the next hop, is happening in the shadow context, not in the default context. This allows us to abstract the position of the virtual route reflector or virtual network function from the actual physical location of data center and let them behaving as it is in the south or north or whatever region we want. There are a couple of aspects which has to be considered. Resiliency. Yeah, maybe it's a good idea to have 2 GRE tunnels and have 2 shadow routers. That's nothing special if we use the traditional approach with the route reflector on the stick. You also connect them usually to 2 core routers, and the selection of these 2 core routers are same, right? It's something which is in the region and has best equally, or very similar cost to all clients. So it doesn't change the design approach we use since last, I don't know, 10 years. It's just we use the tunnel instead of physical interface. We have to avoid for some of you who has experience with the GRE or tunneling, well, generally running routing protocol over the tunnel, it's a call for problem. That should be like a bell, because it may result in recursion, right? So we learn the destination of the tunnel through the IGP running inside the tunnel. So the tunnel will flap and the IGP session will flap because, and then our next hop resolution will be, BGP next hop will be invalid, BGP redraws, and it's a circle of the disaster. We don't want that, and using the separate instances, that's why I use the separate instances, solves the problem. Yes, it could happen for this or other reason that the tunnel destination will be learned over IGP, but this information will be in the context, not used for forwarding of the GRE tunnel packets, so it doesn't hurt. Another security concern with these kind of things is, hey, I want to be sure that there is no traffic passing through my VNF. Virtual machines and the compute nodes are good for the BGP, but that's not the best core router ever. I would say the worst ever. So we at the same time, the shadow instance is a part of IGP. They have two adjacency over two tunnels. So it's a part of the network, part of IGP. We have to prevent the passing traffic through. So yes, we can do this on the control plane, put the high metrics on the tunnel, set the overall bit if we can, if it's ISIS, that's good. But that's not guaranteed that there would be no transit traffic. So the guarantee could be achieved through the filters and the filters applied on the shadow host, so on the ingress of the tunnel in the network, on the network side. Some vendor implementation may make it easier than other, but in generally, that's the general solution. We need a filter which allows only IGP traffic and maybe BFD. And the concept could be extended. We may have more than one shadow instance, right? If we can instruct BGP to use some context RIP or other instance RIP to resolve the next hop, we can say, hey, but we have the RIP 1 for the internet, RIP 2 for the VPLS, RIP 3 for L3 VPNs, and yet another RIP for the next hop resolution for the MBGP, so the RPF routes for multicast. Why not? And each of these instances may have different tunnels, different point of remote points of the tunnel, and because of that, different topology view. We can even create different regions for the internet, different for the VPN, different for the multicast. It's quite flexible. So, in summary, instantiate route reflector as a virtual function could provide optimal routing, optimal to the level it's optimal today, regardless of the physical location of the route reflector. And it's like evolutionary solution toward optimal route reflectors, optimal route reflectors feature set, which is a little bit aside of my talk. I'm not going to talk about this time. Next hop resolution and path selection based on that could be different by the address family. That's possible. That's doable. Depending on your it could be controlled by policy. And protecting the virtual network function of route reflector against unwanted transit traffic has to be considered. It's very important because otherwise we can screw up our, we can overload the software running on the VM with the transit traffic instead of dedicated these resources for the dealing with the BGP updates. That's what I have. Thank you very much. Any questions? There is a mic.
Hi, and we got one question. And on the VRR, is LDP supported?
Is what?
LDP, Label Distribution Protocol supported.
Okay.
We have some like inter-ES option C applications, and which the route reflector, the how do I say, the route reflector for inter-ES option C, the RDP is required to go to the other side. And we heard like RDP is not official.
Let me answer that way. I think I understand the question, so in sake of time. First is the support of particular protocol on the virtual route reflector except BGP is a vendor-specific answer. So I can answer from my company, but let's better do offline.
Okay.
But usually you need the labeled route if you want to resolve labeled prefixes, BGP prefixes. And again, it's a vendor-dependent or software-dependent, but there is nothing which stops you from the standard perspective to put the IGP prefixes you learn in the context into the labeled RIP and let it's a fooling of the route reflector, right? But you can do that, and you're not losing anything. You still have you still trace the reachability of the next hop.
Exactly, and for the reachability validation, and we can use RIP group and to make it work. And so far, it's for the inter-ES option C, he need to go to the other route reflector, and to pass the label and to go through the ESBR to go to the other side is a label switched path, and which require the RDP. And the physical RR can do that. So far, the VRR and the function is there, but I heard like RDP is going to be removed from support from the VRR, and which for us, I think like for the inter-ES
Again,
option
that's
C,
a very vendor-specific question. I can answer it, but
we can go off.
But I think it's not the place. Yeah, I was asked to be not vendor-specific.
Yeah. Okay.
Thank you, Randy.
Right.
I think Randy is.
Yeah. Sorry, Randy, we're going to have to close the mics. We're running behind, and we need to continue. So thank you very much.
Thank you very much.
Thanks. So.